Hi, in this video we'll explore Clip, a very powerful method to connect text descriptions with images. So we're going to understand how the Clip models are trained. We're going to classify images using them using a zero-shot approach, and we're going to create some image and text embeddings with a pre-trained Clip model. We're also going to discuss the use cases of Clip and its limitations. So CLIP stands for Contrastive Language Image Pre-training. This model learns transferable visual representations from natural language supervision. What does that mean? It means that it learns to match text descriptions to images. It was developed by OpenAI in 2021, and it was trained on 400 million image text pairs scraped from the internet. It connects these images and text, their embeddings, in a shared space. And this is something that enables something very powerful called zero-shot classification. That is basically creating a classifier, a new classifier, without having to retrain it. You can find the paper on the further reading links. I recommend that you check it out. It's very interesting. It's one of the most impactful models of the last, I would say, 10 years. Clip then aligns text and image embeddings. What does this mean? We're gonna have semantically similar images and text being close to each other in the embedding space. So if we have a text that is two dogs running across a frosty field, this is gonna be something that is very close to the image that describes this, like the text embedding, the vector that we have created to represent this text is going to be close to the image embedding that we have for this image. This is what Clip achieves. These two vectors have the same dimension, they have the same size, but they correspond to two completely different modalities. So we're going to pull them together while training Clip. And then you see that the text description that doesn't match an image, like an elephant in the Serengeti, you see that it's going to be close to the image of the elephant, but it's going to be like very far away from this image that has the tail of a whale. Like this particular image has no matching text description. So Clip is going to be using text encoders to transform the text into embeddings. Additionally to the image encoder that can be a ResNet or a vision transformer, it's also going to be using a text encoder. And notice how this is encoding the word bank differently depending on its context. Plain banks relates to aeroplane and flight, and a grassy bank relates to grass and fields. Like the Bank of England relates to finance, institution, and money. The context is very important for the embedding of the bank word. This is very similar to what we discussed previously on the video about image embeddings. So good embeddings make semantically similar words close to each other in the embedding space. And this semantically similar thing is about the context. So then we can evaluate this similarity using metrics like the Euclidean distance and the cosine similarity, exactly like we saw before with images. So the Clip architecture has these two components, the text encoder and the image encoder. Each one has its own weights, but they're going to be updated by the same loss function. It's going to be a symmetric cross entropy loss that we're going to see next. So the image encoder can be a vision transformer or a ResNet, and this is the one that is going to be creating the embeddings for the images. So both of the encoders map the inputs to a shared 512 dimensional embedding space. So that means that the embeddings of the text are going to have the same size as the embeddings of the images. And as the embeddings have the same dimension, then we can evaluate their distance using the cosine similarity. These models are updated using the same loss function, so that they are going to be pushing the text embeddings close to their matching image embeddings. And this is how we train. So here we have a batch of images and their corresponding text embeddings. Clip is going to maximize the cosine similarity between embeddings of matching text and image pairs. Consider this matrix, the text embeddings T1, T2, and the image embeddings I1, I2, I3. The elements in the diagonal represent matching text and image pairs, and these are going to have very high cosine similarity. The non-matching pairs are pushed to have low similarity. And here we see the training algorithm. We see that we're using a symmetric cross-entropy loss. What does it mean, symmetric cross-entropy loss? We're going to be computing first the image to text loss and then the text to image loss. So cross-entropy is not commutative. That's why we need to compute these two losses and then average them. This is some pseudocode that I took from the original paper. I recommend that you check it out. It's quite interesting how simple is the training algorithm. So Clip enables something very powerful, which is the zero-shot classification. That means that to classify an image, we can just create a text prompt like a photo of a plane, or a photo of a car, or a photo of a dog. Then we're going to encode these prompts using the text encoder. We're going to be encoding the image using the image encoder. And then we're going to calculate the cosine similarity between all the possible text descriptions that we have. And if we do the softmax here, we're going to get a probability that is going to be very high for the correct class. This is able to classify these new images without a specific training for this new classification task. This is what we call zero-shot classification. We didn't have to train a new model to create a new classifier. We just had to create embeddings out of the text encoder and the image encoder and see which is the one that has the best match. Here we see a demonstration about how to do this using the Hugging Face implementation of the Clip model. This is exactly the same model that OpenAI published in 2021. It's just adapted to the Hugging Face interface to make it a bit easier to use. So we see in the code how to produce the embeddings and how to calculate the similarities. We see here that we can create cosine similarity scores between image and text embeddings. We can print these values. And the example shows how classifying an image of cats using different prompts is going to have a higher probability the more specific we make the prompt. So if we make this prompt being 2 cats lying on a sofa next to 2 TV controllers, this is going to have the highest probability. It's going to have a much higher probability than 2 cats or a cat or a dog, of course. So this is something very interesting and powerful about Clip. The more descriptive you make your prompt to what you have in your image, the higher is going to be the matching probability. It's very useful for semantic search. So we can also control this probability with a temperature parameter of softmax. So by default, we have a temperature parameter equal to 1. And when we lower it, it's going to make the distribution of probability more peak, like closer to giving you just 1 for what is the top probability. And when we make this value higher, we're going to have a distribution that is flatter. It's going to be more uniform. This is something that we can use to control the probabilities that we get out of Clip. It's very useful when we use the model to create soft labels. That means that we can use Clip to create some candidate labels for our dataset and then use a specific model, like a new model that we train from scratch, to create a better classification. That's something that I'm going to discuss why this is relevant next. So In the paper, they did many comparisons in which they took the model, the clip model, trained on the 400 million images that they scraped from the internet, versus a ResNet 101 that was pre-trained only on ImageNet. So if you recall, ImageNet only has about 1 million images, and they did this comparison in which they took the ImageNet pre-trained model and compare it against some variations on ImageNet, like ImageNet in sketch form, ImageNet 2, ImageNet adversarial, like things that are similar to ImageNet and have about the same classes, and they compare the performance. We see that on the original ImageNet dataset, the clip model performs just as well as the ResNet 101, and then in the others, it has some remarkable performance. But consider this: the bit model, the vision transformer model that they're using, has way more parameters. Also, they're training on 400 times more data. So this is something that is expected. And something that is interesting about the performance of clip is that it doesn't outperform, in many cases, simple classifiers or regressors that have been fine-tuned for the task. And this is something that the authors were very honest about, and very interesting is to read the discussion about the limitations. So clip usually doesn't compete. It's not as good as a fully supervised model that has been fine-tuned for a specific task. In this example, we see clip struggling with object counting on the Clever Counts dataset. And there are many other examples where clip is not as good as just creating a fine-tuned model. Like the most glaring example of this is MNIST. If you create an MNIST classifier, just like the one that we have done since the start of the course, you're gonna much more likely get a higher accuracy and a higher performance by creating a very simple classifier than to try to do it with clip. Even then, the model is super useful and super powerful. It's very interesting to use it on semantic search. So here you see a demonstration of FiftyOne. Voxel FiftyOne is this tool to curate datasets, and we can get some really good performance on image search by using clip embeddings. We can relate the text embeddings that we get out of the terms that we want to search with the image embeddings that we have in the dataset. And it's amazing. It performs as you would expect in something like Google image search. Clip also has some very interesting use cases in the guiding of diffusion models. Models like DALL-E, DALL-E 2 and Stable Diffusion are using clip to actually guide the generation process. So when we write prompts like create an image of an astronaut riding a horse in pencil drawing style, what is enabling the model to relate what we want to see with the prompt that we're writing is actually clip. So to wrap up this video, we saw that clip learns joint embeddings. It creates a shared embedding space for images and text, and that these multimodal embeddings have applications on semantic search and image generation. We saw that clip excels at something called zero-shot classification. That means that it performs well on new unseen tasks without additional training. But we also saw that clip has limitations. It's not always better than models fine-tuned for specific tasks, and that retraining clip with a bit base is expensive and something unfeasible for most people, both computationally and data-wise. We also saw that clip learns some very useful multimodal embeddings that have so many applications. I encourage you to try some of them in the accompanying notebook that we have. It's amazing for search of similar objects, searches that relate text with images. We're gonna do many experiments with this using Voxel FiftyOne, and the notebook that I have created, in which you will see how to extract your text and image embeddings out of the Hugging Face transformers implementation.